All right, I feel completely lucky. It was like fortuitous that I was going to do this screencast right now on the International Space Station. I like grabbed my phone. I'm like, well, let's see what's going on with the International Space Station like right now. And so this was at about 4:30 on Friday afternoon, and it just happened to be when I opened my phone app on it that the space station was cruising right by. Near Cairo. So that was pretty cool. And I wanted to just grab the stats here from my phone on the app. Unfortunately, there's not a good sighting. That's what I was hoping to talk about. In the next couple of days, there'd be a really good sighting for you to see. With the lack of pollution, it's really fun to see the ISS sightings right now. So I would encourage you to go online and look for this app. It has this icon, or there's other ISS tracker apps, and it'll get your location and it'll tell you when the next good sighting is going to be, but I don't think there's anyone in the next couple of days. The timing has to be just right because the satellite's so close to the surface of the Earth that as it goes around, it has to be like right after the sun sets. So the sun is still hitting the space station, reflecting off the space station onto us. But it can't be during the day because there's too much light. So it has to be either in the morning, which you probably wouldn't get up for right before sunrise, or right after sunset is good times to see the space station. And even if there's not a good one in the next week or whatever, keep checking on it or turn notifications on, and it'll tell you when there's going to be a good sighting, and that'll be fun. Anyway, we saw there's some data here that it's giving, and I'm using just one of those numbers, the speed, and using the speed, and then also using our mass of the Earth here. And speed's only to 3 sig figs. I'll talk about why that ends up being a problem in a bit. But anyway, so here's the mass of the Earth to 4 sig figs, and then the radius of the Earth, which is part of one of the questions, is given to 4 sig figs also here. And what we're going to do is just use some information about the space station to then use our equations that hopefully you're getting a little more comfortable with in 6.2 to solve some stuff about the orbit of the ISS around the Earth. It looks like we're going to ask for the radius of the orbit. That means from the center of the Earth. From that, we'll be able to figure out how high above the surface of the Earth it is. And then finally, just like how long does it take for the ISS to go all the way around the Earth will be the last thing. I put a link here. This is more of an internet link for your computer to jump to a cool site to look at some data about the International Space Station. But then this phone app is the one I'd really encourage you to do. So that's it. They're not really hard problems. Let's look at how we go about solving those. We're going to go back to the same old equations we've been using a bit lately. And so let's just look at this first one here. So we're going to say that whenever anything's in orbit, that that it's not in equilibrium, that it actually has a net force acting on it. That net force means that, this net force is special because it's a force of gravity, and it happens to be perpendicular to the direction that the object's going. When something's in orbit, its velocity and its acceleration are 90 degrees to each other. So it keeps turning the thing in orbit, but it never speeds it up or slows it down. But it keeps accelerating it towards the center, which means it just changes its direction without changing its speed. No work is being done, so the velocity is changing, but the speed isn't. And that's the idea, because no work is being done. In any case, the centripetal force is given by this equation, mv squared over r. And F net is going to be that centripetal force. What is causing that centripetal force this time is gravity. And gravity, as we know, is given by gmm over r squared, where r here is from the center of the planet to all the way out to where the space station is. So that's not the radius of the Earth, but the radius of the orbit. We can set these equal to each other and cancel little m, which is the mass of the space station. So we didn't need to know the mass of the space station. We need to know capital M, which is the mass of the Earth, which was given, and we're trying to find R. So when we take this R and cancel it with one of these R's, that's why this R squared goes to just being R. This R goes away, that M goes away, we're left with just V squared by itself on this side of the equals. Now we're solving for R, so I'm going to bring the R up over here, bring the V squared down there, or cross multiply if you don't know how to do that algebra. But we get R equals GM over V squared. And now we're just going to plug and chug. So that gets pretty easy. So we're going to plug and chug here. We got G, which we know is this constant. We have M, which is the mass of the Earth. I was a little sloppy with units. I should be putting the units in here. This is in kilograms, like it needs to be. And then for V, we need the velocity, which was 7.66 kilometers per second, needs to be in meters per second. So we're going to go times 10 to the third, and then we're going to square that whole thing because V is squared in this equation that we derived. You'll notice this equation is not in the IB packet, and you need to be able to derive it in seconds easily. And I would not encourage you to memorize it. I would much prefer if you do this process quickly, and you've done it so many times that you just whip it out, and you can get this equation right here in seconds. So that you can use any of these equations however you need to. Anyway, we plug and chug there, and we get this answer of about almost 7 million kilometers from the center of the Earth to the International Space Station. You say, wow, it's really up there, right? That's so far up there. But wait a minute. I think I gave you the radius of the Earth up here. And if we go up and look at the radius of the Earth is 6.4, let's call it 6.4 million meters. So that's not actually much bigger than that. So it's actually not that much farther from the surface of the Earth, which is an interesting question, like what is the gravity field at that height? And that's a question I thought about putting in here, but I didn't. But we could go back to the other equation where we say G, little g, the gravity field equation, and we could plug in and find the gravity field where the International Space Station is. You find it's not that much different than 9.8 because it's almost the same distance away, 6.7 as opposed to 6.3. In any case, if we want to know how high above the surface it is, we're going to need to subtract those numbers. So if we go for the height, we're going to take the radius of the orbit minus the radius of the Earth and subtract those two numbers. Now, when you subtract, you really should only be keeping a few sig figs at the bottom of the subtraction here. So we really should be rounding this all the way up to just 2 or maybe even 1 sig fig. Because if you really only have 3 digits, I guess we still have 2 sig figs, so it's okay here. So we get around 420, but this digit here is really not significant. That's 0, so we round it away. And that's why this rounded to this. Remember, when you subtract, you don't get to keep all those sig figs. Anyway, we get about 420 kilometers for the height above the surface. And if we look back to the iPhone little app here, where did I see that? Height, 422 kilometers. So that's pretty good. Feel pretty happy about that. But I want you to think about that. That's not very high compared to the radius of the Earth itself, right? So it just shows how thin the atmosphere is around the surface of the planet. And the satellite doesn't have to be that high in relative distances to the size of the Earth itself, which is pretty cool. And let's see what's left. I think there was one more question. Oh yeah, well, how long does it take to get around? So now we have V equals 2 pi r over t for any orbiting body. So we solve that for t. We get t equals 2 pi r over v. And we just solve for r. Make sure you use the right r, the one for the actual orbit r, right? Don't use the height by mistake. And then divide this by the velocity. Make sure you're in meters per second. So you have to do that times 10 to the third. Make sure it's in parentheses. Those are the little mistakes you can make. You should get about 5,000–6,000 seconds. And if we want to know the minutes, divide by 60, and you see we get about 93 minutes. So that's pretty cool. The Earth is spinning also during those 93 minutes as it orbits. So since I started this, took this picture back here and was setting up for this screencast at 4:30. We're now looking closer to 5 o'clock right now, but I just wait a little while longer. I could see that it's now going to be in a little bit different space because the Earth has been spinning. But we could look at the picture again and it'd be back here because it's gone all the way around the Earth in 93 minutes, which is pretty cool. Which is why it's fun to watch from Earth, and you watch it go across the sky right after sunset. You can see it moving across the sky as it's orbiting the entire Earth in every 90 minutes or so. So ISS, very cool thing. There's great YouTube videos showing what it looks like from the ISS, looking at Earth, and that'd be a cool thing to do for a minute. But I'm going to stay on task here, and maybe I'll put a link to that. But this screencast is done. I hope that helped you out a little bit, and you are getting better at how these 6.3 equations work and how they tie into centripetal force and the orbits of objects in the solar system. So good, and see you soon.